and Mihaly for the invitation. Welcome. Thank you for being here. I know it's the tail end of the semester, so we're looking forward to actually end the semester and go back and enjoy some family time. I put together, as Nick said, I've worked in many fields. I came actually to the States in 2004. I worked for the government in Washington, D.C. At NIST. Then I went down to Georgia Tech, concluded my PhD, worked in a startup there as a chief scientist, and now I'm back in Georgia Tech as an assistant professor. Which, the lesson here is never piss off the people you're working with in the university. You never know. You might end back to the same university. So today, I'm going to try to provide you a breadth first look at the DNS. Sorry for that. And see how you can actually use DNS in order to actually deal with abuse in general. I've done many papers. I've worked with many papers on DNS, and the common denominator across all my work is if you have nice underlying network data sets, in this particular case DNS data sets, you can actually do some pretty interesting stuff. Throughout my pretty much a decade work on the space, I've realized that not many people can actually get access to these data sets. So I will conclude my talk by opening some very interesting data sets to you, and of course to the rest of the community, by a project that we actually concluded a few months back. Nick already actually has access to the data, but if you see something interesting from this talk, please reach out, and we will give you access to these data sets. So how many of you know what DNS is and what DNS does? Great, fantastic. So this is a slide that I can actually go through very, very easily. I'm going to just provide some basic terminology around DNS so we can actually, be on the same level. A client, like your laptop, will actually initialize a standard DNS resolution request. In the DNS nomenclature, this actually is referred to as the stub resolver. And typically, it will try to connect to a recursive DNS server or server farm, depending on where you are. I suspect a university like Stony Brook would actually have a few servers that actually act as the caching servers, as they say, between you and the rest of the internet. The rest of the internet being the root servers, the TLD servers, and the authority name servers. And we need those recursive DNS servers in the middle simply because we don't want to actually overload the upper layers of the DNS hierarchy. And by upper layers of the DNS hierarchy, I mean the root, the top-level domain name servers, and the authority name servers. In the event where your DNS resolution request misses the cache of the recursive DNS server, it would actually proceed into an iterative process through which it would actually reach the roots, the TLDs, and the authority name servers in an effort to actually derive the proper mapping between a domain name and an IP. And that's what the domain name system actually does. It's a distributed hierarchical database through which you can quickly map a domain name into an IP address. The question, of course, here that we have to actually answer is how that helps us in identifying abuse, identifying and potentially stopping abuse in the real world. In order to actually answer that question, we need to actually take a step back and see what the garden variety of infection looks like. And if you have taken both Nick's and Mihaly's classes, you will actually realize that everything starts by the exploitation of a vulnerability. Think you're a casual user where you actually just visit a domain name, a website that has some sort of an iframe that actually tries to exploit the vulnerability in your browser. The moment that vulnerability gets exploited, the first thing that would actually happen is some sort of a payload will actually dropped into your stub resolver, into the environment of the stub resolver, effectively your laptop or your machine. When that happens, the first thing that this first stage dropper will actually do is check whether you are a legitimate user or you are some sort of researcher, for example, from Georgia Tech, who does that in a regular basis and try to actually milk that for the purpose of research. So basic checks, is this, an infection or another space or a host that I've never seen before? So if everything is kosher and we can actually see, this looks like a legitimate infection, there is no red flags. The second thing that would actually happen at that point is a more sophisticated piece of malware or the second stage dropping action will take place. And at that point, the core botnet agent will actually get deployed into your host, all right? And of course, from the point of view of efficiency and in order to actually make the forensic operation harder from the point of view of the white hats, the first thing that the malware will actually do, the sophisticated malware will actually do there, is clean up after itself and try to attach itself into some sort of a benign process. Internet Explorer, your calculator, or whatever, in order to actually make the remediation of the host significantly harder. And of course, when that is successful, then the key point of the malware will actually come into place, where, for example, it could actually easily exfiltrate data to a remote location. That data could actually be passwords, credit cards, whatever happens to actually be available at that point on the system. One thing that many people actually forget is that this is not the sum of your problem. This is not where everything ends. When that goal has been achieved by the malware, then you actually have the adversary constantly having the ability to actually remotely control that infected host and utilize it for a number of other activities. In other words, that host is a piece for monetization activities for the entire, for the bot master itself. So you can actually use that host for a number of other activities like click fraud, Bitcoin mining, or however, SEO, such as optimization activities, or however else the adversary can actually make money through it. And as you can actually see, in every key piece of this typical threat lifecycle, you actually have the network to play a very important role in the entire ecosystem. Either the first stage or the second stage dropper or the monetization activities of the malware will actually have to reach out to the broader internet in order to actually engage, in order to actually facilitate the criminal activities or the entire botnet operation. So this is a huge opportunity for us as defenders to go ahead and try to actually flag which were the domain names that the binary is actually using in order to get dropped to the particular host, or to actually communicate with the broader internet, or to download the very sophisticated malware, or to actually perform monetization activities. Therefore, intuitively, if we have a way to effectively create a grayscale or deal with DNS abuse in an efficient manner, we can actually control the overall abuse of the internet. Why? Because we can actually potentially block those actions before they even happen. All right? So let's try to actually see how DNS and the analysis of DNS traffic can actually help us achieve that. All right? So the first two, today I'll try to quickly go over 4 papers. I'm not going to go obviously in detail because that will actually take us more than an hour. But the first 2 papers would actually help you understand how we can actually mine DNS in the context of a graph. How you can actually take successful and unsuccessful DNS resolutions, create graphs, and use spectral methods to actually quickly analyze this traffic and create detection profiles for certain types of abuse actions. Okay. In the third paper, it will give you a sense of one of our latest works on the trust of a domain name, and how people can actually misuse that trust. Very simple way to actually think of this is that if a domain name is already trusted by the community, so for example, you trust google.com, am I right? So if I send you a link with google.com, you will click on that link, am I right? That's logical. If google.com expires and I register google.com and I put a malware on google.com, what am I doing? I'm exploiting the positive residual trust of the domain name making you my victims. All right? Of course, Google has very good teams, and they won't allow their domain name to actually be to expire. But there are other domain names that exist for many, many years, and it's easier for them to expire. And when they expire, then illicit users can actually take them over and utilize them in the context of abuse. And we will actually see what is the prevalence of that activity. Last, I will briefly touch upon this active DNS concept that we presented recently in RAID. And that is a system that we actually built in Georgia Tech in order to actually give to the rest of the academic community data, DNS data that you can actually use in order to conduct research, repeatable research, in the context of DNS security. So these are free data if you want to actually work in this space that you can actually utilize. But let's start with the first two papers, Notos and Pleiades. And in order to actually do that, we need to actually first establish the notion of this bipartite graph, or as we actually discussed this in the paper, the notion of the passive DNS replication, or passive DNS reconstruction. Passive DNS is nothing more than the sum of your successful DNS resolution that you can observe in a given network over a period of a day, let's say. All right. As you can imagine, when you're visiting when you're visiting a website, you're engaged in a DNS resolution between a domain name and in the network traces, you actually have evidence of a domain name pointing to a particular IP address. All right. Steering that up in the context of an entire organization, or even better, in the entire telco, an entire internet service provider, for example, and you get things like this. All right. In this case, you can actually see the related historic domain names and the related historic IPs based on a resource record. A resource record in the DNS notion is a mapping between the domain names and IPs. That's the fancy name they use. Between an Akamai domain name and an Akamai IP. Let's try to actually see what the passive DNS view will give us in the context of this graph. If you take, for example, the zones under this that actually have the Q names that historically have been linked to this IP, you can actually see a very homogeneous structure of domain names. Why it's homogeneous? Because you actually have effectively the same second-level domain, akamaiedge.net. You have some small variation in the third-level domain, all right, and some higher variation in the fourth-level domain. Can someone tell me empirically what this really means? An operator in Akamai did what? Went to register a domain name and structured the zone in the context of what? Of that particular IP. All right? He said, I manage this zone and I point domain names under the zone to this IP. Why he did that? We will examine that in a moment. But that makes sense, am I right? Let's go the other way around, when we actually take this domain name and we see the IPs under this domain name and the zone that we can actually observe according to the passive DNS observations. Can someone tell me what is common around this set of IPs? They are all in the same /24. All right? So, piggybacking on what we just said about the zone, you have a zone that was structured in a way and pointed to a particular /24. Why? Because the operators in Akamai, they try to effectively, properly manage a zone. That's what Akamai does. Quality of service and uptime. That's what they offer. So they structure their zones and then IPs in a way that they can actually manage that long term. All right? Very, very professional, very, very, very reasonable. On the flip side of that passive DNS view, you have a domain name that is actually historically linked with, back then at least, with activities around Zeus. Everybody knows what Zeus is? It's a banking Trojan. This was actually a CNC for Zeus. So if we do exactly the same analysis here, you can actually see that you have one IP and a bunch of different domain names pointing in that IP according to our passive DNS traces. In this case, we actually see the operators of Akamai try to maintain a reliable infrastructure. In this case, the operator of this network and domain name zone, what is trying to actually do? is trying to actually burn through as many domain names as possible until the IP gets blacklisted. Can someone think why? Why he's trying to burn through a lot of domain names versus burning through a lot of IPs, for example? It's cheaper. Why? Because IPv4 is finite. The domain name space is countably infinite. So it's cheaper, so you can actually go and blacklist the first 3, 4, 5, 6 domain names, but still that host might be active. So you can actually piggyback other domain names in your malware CNC list, and you can rotate them until all of them have been burned by the defenders. Now the question here is, this basic intuition, and of course, we can actually go into multiple other intuitions around the same, domain name and IPs, but how we actually convert this intuition into something that we can actually scale every day. We cannot have threat analysts, we cannot have researchers trying to reconstruct things like that every day in order to actually deem what is legitimate and what is malicious. Can we have an algorithm do that? Of course we can. What is our challenge? Our challenge is to actually move from this categorical space that we actually have here, which are domain names and IPs, into something that actually fits into a function very, very well. And that's where we actually do feature construction. All right, statistical feature construction. So in this case, you can actually say, well, what are the properties of this, related historic domain name set and related historic IP sets? Where in this particular case, you have one /24, one autonomous system, one owner, and several IPs. In this case, you have one zone, a few second-level domains, a few third-level domains. And you start building features like that you can actually represent into an n-dimensional space. All right? When you do that, you effectively get both features that actually you can use around zones and features that you can actually use around networks. And you also can actually do things like build similar features around evidence. And what are the evidence that we actually have? Those domains and those IPs might be witnessed in malware traces, in the dynamic analysis of other malware samples. So you can actually say, well, these zones, you can actually see a few malware samples actually reaching out to those domain names or those IPs. And that actually plays into a new evidence-based feature that you can actually compute on the fly. That is the critical thing here. All these features, each one of these features is not strong enough to independently go and classify an action. In aggregate, though, you can actually create a hyperplane that actually includes all the particular, malicious behavior or low reputational domain names, if you will, for a particular period of time. All right? This is very, very scalable, especially when you are dealing with distributed file systems like Hadoop and Spark and things like that. And when you actually build those features, a couple of network profiling and domain clustering modules will actually help you build a reputation vector that is quite efficient. I'm not obviously going to go into the details for the interest of time. What I will try to actually say, though, is that once we actually build a system for day one, let's say, and we actually pick a threshold of any domain name that was low in reputation, 90%, for example, has we have 90% confidence that the reputation is low, and we can actually use that as a cutoff filter. We can actually early predict domain names that end up eventually in public malicious blacklists, weeks and even months before the particular domain name was actually listed. And that actually has a variety of different, that includes a variety of different cases, both from the point of view of exploit domain names, malware, and other type of traffic. Point being, you can very easily every day create a grayscale, pick a threshold, and start flagging potential domain names for abuse. And that is something that we really want to do, especially if you are a large telecommunication network, because you can actually have a sense of what is the level of abuse in your network. All right? You cannot scale that up in the context of manually creating blacklists, but a system like that can actually help you, scale that up in the context of the entire traffic that you actually see on the network. A couple of years after we actually created a system like that, there was a completely, back when we created this system in 2010, malware tend to actually utilize a few domain names, 1 or 2 domain names for command and control. Okay? So the malware author, what it will do, it will compile in the binary, within the binary, it will actually have 1 or 2 or 3 domain names. If the first domain name gets flagged, it will use the second. If the second domain gets flagged, it will use the third, so on and so forth. After this actually was implemented in a large telecommunication company in the States, we actually saw this. The rise of a lot of malware employing an algorithm through which they will generate randomly looking domain name every day. Very smart if you think about it, because that will actually ensure the adversary that every day, given a seed, which could actually be the day, for example, and given an algorithm that is embedded in the malware, it will generate a new set of 1,000 domain names that could actually potentially be using every day. So would a system like Notos help us in that case? Absolutely not. It would completely fail. Why? Because the key principle that we said that the Notos is actually using is the historic evidence that you actually have on the network. I think this must be the first talk that the author is actually bashing his own paper, in the same, within like 5-10 minutes. But, that's the game we're playing. We are always behind the 8 ball, so we're trying to actually keep up with the adversaries. But when they actually start using these DGA algorithms, they have a small problem. They are using the algorithms so they can actually register 1 or 2 or 3 domain names every day, so we cannot predict those domain names unless we have both the algorithm and the seed. In order to get the algorithm, that is really hard. Why? Because you need to get the binary, reverse engineer the binary, and try to reconstruct the algorithm from the reverse engineering. How many of you know how to reverse engineer a malware? Exactly. Well, you don't count. I mean, you're teaching here. You should know that. You should know that. So point being is it's extremely hard. All right. So if it's extremely hard, that is something that the adversaries are actually using in order to actually play this against us. Now, what we can actually use in our benefit? Well, if they are using, let's say, if they are generating 1,000 domain names every day, and they are registering 3 domain names, all right? The 997 domain names will still be resolved, am I right? They have to. Why? Because the binary do not know which one of those domain names is registered, so they have to exhaust the domain names, or at least start exhausting the domain names up to the point they hit one that resolves. All right? What happens when the domain name that doesn't resolve come back? What can we observe in real traffic? An unsuccessful DNS resolution. Okay, let's go away from malware for a moment. When do we observe unsuccessful DNS resolutions in our networks? Yes, sir. Typos, exactly. Nick is here. He would be freaking out if you hear an answer. Of course. Typos is another one. Typo is, statistically, you go to Google, you're in a hurry, or the coffee spilled over the keyboard, something happens, you go somewhere else, hopefully not getting infected. Point being here is it's extremely rare, and it should actually be around a space of something that is a popular domain name. How often you think a randomly looking domain name, okay, is being queried twice in the same network in a day? Could a human do that? Fantastic. That's our second paper. That's the Usenix paper around the detection of DGAs, which actually is based on this exact principle, that you would actually have unsuccessful DNS resolutions in a network that is so rare that you cannot actually have 2 humans doing that at the same time. All right? Of course, the question here is, again, how you model that and how you actually take that and put it into operational environment. So we actually do that in 2 steps. The first is a DGA discovering phase. In other words, we don't have the malware, we don't have the DGA, we don't have the algorithm itself. So from raw network traffic, we need to derive that algorithm, or to be more precise, a statistical approximation of this algorithm. So we can actually use that the day after. Okay? So we detect it today. If tomorrow morning we want to go into the network and detect the same algorithm, we need to know how we can actually do that. All right? So that's a DGA discovery phase. And the DGA modeling phase and classification, once you do that, in live network traffic, how you can detect both the DGA and the active domain name. Yes?
So just to clarify, there are lots of other network services that may send out, lookups for domains that look malicious, like a mail server, right? And it's quite frequent that you'll have primary and a secondary mail server perform the same lookup with it, back to back. So would you whitelist those, or do you have some other way of figuring out which ones are?
I don't know. Your professor here, or your IT staff, or something? How do you know that?
I try to pretend to be.
What? The first or the second? The first? Well, you have clearly operational insights that very few people have. What? Your name? Mike. What Mike said right now is one of our major first false positives in the system when we deploy that into a large telco in the States. The beautiful thing, though, with that is that there are only a handful of mail relays or huge NAT points that would actually exhibit this behavior. So from the point of view of the spectral clustering that I'm going to talk in a moment, those look like Death Stars. So it's very easy to identify those few points in the real network that would actually exhibit this behavior. And even when you're seeing that from the point of view of mail relays, you will not see randomly looking domain names necessarily. You will actually see domain names that spammers are having into their mail campaigns, but they haven't registered yet. So the spam campaign has been sent out, and the spammer is a few hours behind the actual spam message. I can give you details around that, why it's happening, but that is the most cases of NX domains that you would actually see from the point of view of a mail server. But when you're talking especially in a residential network, you don't have too many mail servers. You would have only a few mail servers. So they will tend to actually cluster each other, and they will have very little, if none, if any, overlap with actual DGAs that the end host in the residential environment are actually querying. So imagine the overlap between the domain names that the mail server will actually look up and the domain names that DGA will actually look up is pretty much none. But themselves, they will create a cluster according to this. That's a very good insight. And now there is another one, another great case of a false positive that I will actually talk in a moment, that pretty much everybody in the room most likely are using even now. But I will go that in a moment. So let's try to actually see how we actually do the discovery of the DGA on the fly. We are using two different techniques, one spectral and one clearly statistical. And the statistical is very similar to the things that we just talked about earlier with Notos, all right? The structure of the domain name. Key intuition here is how you can actually use the structure of the domain name in order to actually create a statistical vector that you can actually use every day to represent these clusters. These are two real-world clusters from two different malware families that we actually observed back in the day. Can someone help me identify these features that we need in order to actually model those domain names? So, first of all, let's go for DGA1. Is it safe to assume that these domain names look the same? Like, visually, they look the same, am I right? It's something does something .ru or .com, all right? Well, this something dot something, how we express that statistically? N-gram analysis. Everybody understand what n-gram is? N-gram is what is the frequency of the two characters if you just have a sliding window over the domain names. All right? That is something that if you model this frequency across the entire set, it would follow distribution. This distribution will be effectively the distribution that is derived by the domain name generation algorithm embedded in the malware. All right? How we actually do that at scale? Well, you compute 2 grams, 3 grams, 4 grams. You compute entropy, which effectively is the 1 gram entropy, and you actually take into consideration the DNS structure itself, the structure of the domain name. In this case, you actually have some frequency on the first level domain names, another frequency on the second level domains. Very simple, very nice. The same applies here, okay? So in here you actually have huge variation of the TLDs, huge variation of the second level domain names, pretty stable variation on the third level domain names. Anybody knows what those second domain names, what those domain names are? Dynamic DNS. Why someone would actually use dynamic DNS instead of other domain names? It's free. Very good. So, fantastic, huh? Do you remember the ROI that we're talking about? You actually have an algorithm that every day generates domain names, and your cost of registering domain names is 0. Fantastic. All right? Great. Again, these features can actually model both cases, and how you can actually, cluster those every days. Off-the-shelf XMIN algorithm, you end up having clusters that share the similar structure of domain names based on the unsuccessful domain names that you actually see per host. All right? Step number 1, we have those clusters. Step number 2, let's go back to what Mike was actually telling earlier. Can we actually utilize the way NX domains are being looked up from the network itself? In other words, I want to know what are the NX domains that my domain name, my machine generates versus Mike's machines versus Michael's machine. So when we do that, then if we have a correlation, that means that the three of us most likely are running something that caused the unsuccessful DNS lookup of a particular domain name. In the context of a large ISP or a large network, this means that you can group together NX domain names that have been queried or generated by the same herd of assets. Okay? And host by assets, clients effectively. Alright? When you do that, you create communities that share the same host that look them up. If you overlap the two, then you actually have highly correlated clusters of both NX domain names that share hosts and structural properties. And that's how you derive DGA domain names for algorithms you don't know. And you don't need to know. Why? Because every day you can reproduce this clustering process only by your network traffic. Your network traffic and the algorithm that you are using. Yes?
So once upon a time, we had like peer-to-peer botnets and hybrid, where you have both sort of peers as well as centralized servers, right? Do you sort of expect to see an evolution where now we have a peer-to-peer sort of network where we each ask just maybe a couple of questions, and then we share the DGA results, so that an aggregate, you sort of lose this mass NX error at any given point.
So the question that Nick is actually asking is that why we are not seeing effectively more peer-to-peer, or what is the relation between peer-to-peer and DGA behavior in a network. The reality is that the most sophisticated bot agents right now, for example, the Zeus bot agent, would actually use both. It would actually use peer-to-peer and DGAs. And why they would actually do that? For the very simple reason. If you try to infect hosts in a residential network where the perimeter policy is very loose, peer-to-peer works great. So you don't need to engage in any DNS communication at all in order to establish CNC or anything like that. However, if you try to actually infect a customer environment or some sort of a business with a peer-to-peer botnet, peer-to-peer traffic in such an environment, it's typically blocked and very easily trackable. So what they would actually do is the moment they actually see that the peer-to-peer network cannot be established, they will have a plan B, which actually goes back into the DGA algorithm. That happens with both the ZA, the Zero Access Botnet, and the Zeus botnet. So the two most sophisticated, more high revenue, if you will, botnets, they actually utilize both because they're very redundant. They're very resilient to takedowns, and it's a huge investment if you think about it from the point of view of the broadmaster. If you're spending so much time infecting and maintaining this infrastructure, they won't actually be, up for as long as possible. So I can see them coexist very easily. I don't think it's a choice. Why they would choose between the two? It doesn't make any sense. Their end goal is to actually remain up and running for the longest possible period.
My question was more like as avoiding systems like Pleiades.
Well, there are systems like Pleiades. There are systems that actually detect peer-to-peer. So they try to actually, try to bypass. If possible, they would actually try to do direct IP communications. But those direct IP communications, it would actually be very untractable in a very locked down environment. Why? Because if you're maintaining logs for DNS and flow, your number one task is to match the DNS with the flow. And if you suddenly see flows that match no DNS traffic, what is that? So you won't do that. So depending on what is the outer goal of the malware, it's not one size fits all. I don't think that's the case. The reality is they have a plethora of weapons that they can actually use, and they will pick and choose what is right for the adversarial model they have in mind. Any questions? Very good. So I'm falling a lot behind, so I'm trying to actually go as fast as I can, despite the fact I have only 15 or 20 minutes more. 20? Oh, okay, I'm not that bad. So after we actually do that, we filter out known DGAs that we've seen before, and then we push everything into the modeling phase, where at that point, we need to actually sort out the legitimate DGAs first, similar to what Mike was actually saying previously. If you have a cluster that you know that would actually cause a false positive, you actually remove it from the modeling action. There is also one other class of benign DGAs that when I saw that, I was completely surprised. That was actually a DGA. Can you think of a very popular software that you're actually using that has a DGA built in? Yes, it's Chrome. So Chrome has a DGA built in. Can you think of why Chrome needs a DGA? Definitely it's not for a CNC, am I right? I mean, obviously. They have everything they need. So why Chrome would actually need a DGA? In order to test the network environment. If they generate domain names that do not exist, and suddenly those domain names point somewhere, what is the problem? Someone is manipulating the network traffic. Why Chrome would care about that? For the ads. Because if they manipulate the network traffic, there's a fair chance they're manipulating the ads. If you Google Chrome ads manipulation and X domains, you will actually see some popular open recursives who are effectively were hijacking ads.
I think they do that to detect if you get one of those portal pages when you look into
That's also the case, but in the vast majority of the cases, I think it's around the ad. We can talk more about that offline if you want. But point being is, there are reasons where benign DGAs exist for a variety of engineering or other decisions, and you can actually count for that, and you can actually model that using the statistical features that we actually talked about earlier in the discovery phase. And when you actually do that, then you can actually proceed directly into the detection of the live detection of DGA events, DGA detection events, where in this case, the goal is to not only detect which host is potentially infected by which cluster, type of cluster that you actually have seen, but also figure out which is the live domain name. Now, the live domain name becomes a bit more complicated. Why? Because you're not dealing with unsuccessful traffic anymore. You're dealing with successful traffic. And at that point, you actually have a valid mapping between a domain name and IP address. In order to actually solve that problem, you need to actually come up with a more not so trivial way to actually model it. We try to actually do a left and right Hindenburg model that actually takes the domain names in the cluster and tries to actually see the transition probability between characters in the DGA. Not very efficient in certain cases of DGAs, but in other cases of DGA, it's quite efficient. I will show you some results at the end. Point being is that this is a very good way to actually detect the live domain name that's been resolved in a particular day. And why this is very useful? This is very useful because if you do that, you can add it temporarily in a blacklist and effectively block the command and control channel that the malware is actually using. Vis-a-vis, there will not be further damage caused by that particular malware to the end host. Okay? So that's a very desirable operational outcome for a system that you want to actually run day in, day out. All right? Some results around the system. The first time we actually operated the system, there were 6 known DGAs. Why? Because these were the malware families that were reverse engineered by the community. The first clustering approach that we actually did, we found 6 more. So a single experiment doubled the number of known DGAs that were active in a network. That is the power of effectively utilizing your domain knowledge and the DNS data in order to actually see what else is actually goes under the radar when it comes to network defense. All right? These were samples of the DGAs that later they were reverse engineered or pointed to associated with malware throughout the industry. When it comes to detecting the actual CNC, which was not our primary goal, in some cases like Zeus, we did very well. There were some other cases like the Banana malware family, Tank Patch, that we didn't do very well due to the structure of the domain name. If a domain name is not as random as we want to be with respect to the Hindenburg model, we are not doing very, very well. But still, in certain malware families, we actually were very, very good. So if someone wants to actually look into this, I would highly recommend this being a perfect next step with respect of the system. So I will try to actually, we talked about, the DNS abuse with respect of successful and unsuccessful resolutions. Let's try to actually go a bit deeper on the point of the trust of the domain names before we conclude. Let's start by, defining the residual trust, and I think we actually talked about this. It's the historical reputation of a domain name that is implicitly transferred with the changes. And we actually gave an example with Google of positive residual trust. And the negative residual trust is effectively the opposite, when you actually have a domain name that's actually associated with malicious activities, and suddenly that domain name is actually become available to the market, and someone can go and register. If you register it and try to actually use it for a benign reason, you will have problems because most likely you're already in a blacklist. You will not be able to actually use it. So let's try. The goal of this work was to actually study that in the context of the entire, landscape, the entire, DNS landscape, and over multiple years to see, do people actually exploit these trust chains? It's a very covert way, and it's very hard to detect when the domain name actually changed from one owner to the other. So we try to actually, do that in a very efficient way. So motivation around this, and I quickly go over just one example. Benedict University actually had one of their secondary name server expired at that point, and it was registered by an SEO company. This means that the SEO company had access to the entire zone of the Benedict University. Why this is bad? Well, they can actually see all the domain names, they can actually see all the emails, they can actually control and inject new domain names under that zone without pretty much anybody else, need to know. So it's a very, very bad both privacy and, of course, security violation. And they actually, they had to actually, go through a process in order to take the domain name back. But clearly, we cannot actually have this be happening in the real world. Another case of expired domain name was, believe it or not, a domain name from a point of contact of an entire RIR was expired. RIRs are effectively entities that actually control entire address space. So if you have the domain name expired, you can actually issue a password, renegotiation. So you effectively can control an entire address space just by having access to a particular domain name. That's pretty bad. because you can potentially control entire autonomous systems and what is effectively policy decision happening on those autonomous systems. Something that Nick would appreciate a lot, expired domain names on browser plugins. We actually did a study, and we actually saw that several of them, or roughly 5%, were expired. So if you want to create the next PUP malware, the only thing you need to actually go and do is go and actually register expired domain names for browser plugins, and you suddenly have direct access to the browser of the entire base of that browser plugin, just by registering a domain name. You don't have to actually infect anybody. It's already infected. Infected in quotes, because they have installed the browser plugin. So you can imagine how bad is that. Something that Michaelis will actually like a lot, a domain name that was actually used for a third-party software in Debian was actually expired. They changed the domain name. It was in the main Debian repo, so it was actually registered by someone else. It had the potential to actually go ahead and update everything, including the kernel or anything else in that system, just by registering a domain name with the cost of $10 or something like that. So in order to actually, as you can actually see, this has multiple implications. Go from the point of view of software updates, browsers, policy, email, everything. So yes.
So why don't those domain registrars have a policy that says if a domain expires, I should double check with you?
They do. It's a 90-day policy. So they try for 90 days.
So all these entities, they didn't bother for 90 days?
For 90 days, nobody came. So they send emails, secondary emails, third emails. It's the RGB period, as they actually is known. It's a grace period that the domain name goes through. And the owner, the registrar is trying to actually reach out to the owner. But for whatever reason, the business went south or whatever, or pure negligence, the domain name won't expire. Yes?
Is there a mechanism where, through mutual understanding, so the registrar will say, these domains are too dangerous to put back into general.
Who defines dangerous?
You've been involved in malware, in botnets, so on and so forth.
So you're telling me right now a registrar who has margins, very thin margins around, selling domain names, they have to maintain a database of malware and public blacklist or critical domain names. And who defines what is a critical domain name?
Your answer is no.
In a hypothetical parallel universe, maybe. In the real world, where people actually, have very thin margins, especially in this space, they just don't have the resources. They don't have resources to deal with abuse. So if I contact a registrar and say, this is a domain name that's actually involved in banking, thief, banking abuse, they will come back to me in a few days. Because they don't have a good enough abuse, team handling that. And you're telling me that they should actually have proactive, that's just not, that is something that I could implement. But you have, everybody knows what ICANN is. ICANN is effectively fantastic. But at that point, ICANN is not independent anymore. ICANN is actually suggesting policy. And, when a regulator is actually suggesting policy, you have all sorts of things come into play. And that is something that nobody would actually appreciate, I think. Yes?
So what is the mechanism that they're required to pursue within that grace period to notify?
I think emails to the secondary, the email that was actually used to register domain names, and I think physical mail to the address during the registration. These are the two, and phone calls, I think, as well. Because if you think about it, if you given wrong information for whatever reason, or if you just change address and you forgot to actually update your email address, your registration address, then all bets are off at that point.
Well, it just seems odd that the contact information for an expired domain may go through potentially expired domains, right? So they're no longer resolving those addresses because they've expired, but most likely the address which is registered is going to be within
Yep.
the domain.
But if that is the case, now number one, how you check that, how you preemptively check that you have a secondary email address that is not valid anymore or who expired or whatever, and number two, how can you validate that the address that they gave you is actually right? At that point, the only thing they care about is, do you have the $10 in order to actually register the domain name, and that's it. That's the crude reality. And that's how the internet was actually built on that principle, am I right? We want to make it as easy and as, the internet, the domain name itself is not built with security in mind. Security is an ad hoc thing that actually comes on top of everything. And we actually see that, after, a few decades of running, DNS. And we actually see that extensively only the last decade when abuse is actually, is going through the roof because we cannot deal with it. You see what I'm saying? Yes, the supporting evidences are here. So we actually took 180 million unique domain names that was expired over the last half a decade. Actually more, I think. Yeah, 2008. Almost a decade. And we actually had roughly 30 million samples that was analyzed between 2009 and 2015 that actually gave us 6 million unique domain names that were queried by malware. And we actually had all the public blacklist data since 2009 that gave us roughly 320,000 domain names. And we tried to actually overlap these two sets with the major 180 million expired domain names over the decade. And these are the results. What you need to pay attention are the two numbers here. This is effectively the overlap between the malware domain names and the domain names that was expired. And this is the overlap, this is the overlap, 100,000 domain names between the public blacklist domain names and the domain names that expired. I would pay more attention to this number. Why? Because in order for a domain name to be in the public blacklist, typically a threat analyst has to put it there. So I would trust more this number versus this number, because this is pretty much anything that the malware looked up. All right? Could it be a variety of different things? We did some filtering, benign filtering that is, but it's impossible to actually filter all the benign traffic. But this, because it's manually curated, holds more value. So pretty much almost one third of the public blacklist domain names, they were part of this expired domain name set. So it's clear that this is a problem, that something is actually going on there. And the big question here is, which one of those were actually registered first, used for a benign activity, and then expired, versus which one of those were bad and then were expired? And I'm almost out of time, or 5? Yes. And that's what we actually try to study in this paper. And because I'm running out of time, I am trying, here we are. These were the numbers that were abused before expiration, all right? This is the combination of the set of the malware and the public blacklist. And these were the numbers after the expiration. So you would expect that after expiration, that is a clear instance of something was actually good and then was actually expired. So that is something that is troublesome. Someone is trying to utilize the previously positive residual trust of the domain name in order to confuse either detection systems or the threat analysts who's actually looking at these domain names. Because if you see a domain name and it's actually registered for, let's say, 5 years, you will say, well, it's out there for 5 years. It's unlikely that it's actually now used for abuse. Little you know that the domain name happened to expire, and you just took the domain name just before just after the expiration period. All right. So if we want to actually look at this in the grand scheme of things, this was a very rare phenomenon. At the end, these are the ranks of the domain names that were expired and used for abuse since 2009. These are the Alexa ranks. And the yellow are very popular domain names. Yellow are domain names between 100 and 1,000. Top ranks are Alexa, and blue are between 100 and 1,000. And you can actually see that historically, this was very rare. But over the last years, This is very, very, very frequent. This is very common phenomenon. And this actually plays even more on lower ranked sites, sites effectively that do not end up being the very high ranks of Alexa, most popular domain name list. So this is clearly a behavior that's actually is happening right now. And I'm almost out of time, so the only thing I'm going to say next is we actually use a very lightweight approach in order to detect that does not need whois analysis. If you have whois analysis, it's deterministic. How you actually realize that the previous owner goes from A to B. But because whois is extremely expensive and hard to get, we actually only use passive DNS traces in order to actually do that. And this very simple algorithm actually can yield that. The features that we're actually using are three. We are monitoring infrastructure changes, we are monitoring the lookup volume changes, and we are monitoring the start of authority, or the authority name server changes, if you will. And it's actually quite robust. I'm running very, very high because I'm completely out of time right now. Here is the rank that we are actually suggesting, and how many days before the expiration we were able to observe this. Bear in mind that we would like to be as close to zero as possible, because we want to prevent an abuse action that happens between the point that the domain name was expired and the point that we actually flag it as potentially abusive. So the closest to zero we are, the better it is. Unfortunately, because the passive DNS traces that we actually have are not as complete with respect to the entire internet, we are actually doing decent well, but not extremely well, as you can actually see here, because it might takes us like several days up to a couple of months in order to detect something as potentially abusive. Some of the discoveries that we actually did, and I'm going to conclude with this, is this. This is one of the most interesting discoveries. There was a targeted attack that happened here in the States by a Chinese actor, a PLA unit, 621486. The people who actually discovered this wrote a report, they released it, then the domain names expired. When those domain names expired, what happens? You have victims that try to reach out those domain names. So what we did, we registered those domain names. And suddenly, we had control over infected population in, I think it was India or somewhere that were actually targeting the attack. It was a research lab. So with $10, you could actually have access. Of course, you should not do it, of course. We did that to illustrate the point. We actually notified the user after. But with $10, you could actually have access to an entire, the byproduct of an entire APT operation. If those things that I said today were interesting to you, I would suggest that you visit activednsproject.org, which we try, me and my students, to actually go ahead and actually open these datasets for the community. Getting access to DNS datasets is very, very hard. If you're doing networking, if you're doing machine learning, or if you're doing security, of course, I think you will actually find these datasets very, very interesting. We had to build an entire infrastructure at Georgia Tech. We are every day generating roughly a couple of terabytes of DNS data, and we have a Hadoop cluster that reduces that to roughly a few gigabytes that you can actually obtain in a Navro format. We should going to change it to Parquet format, so you can actually play with that very, very efficiently. So if you are interested in this, please, drop us an email and get access to the data and conduct research with DNS. We would love to actually facilitate that. And I'm sorry I'm over the time. So I'll take questions from this point on.
Are there any questions? Okay, I guess you were very thorough.
Or very quick and nobody figured out anything.
If you want, you can also ask them outside.
I'll be here. I'll stay here. If you need anything, please come and find me. Thank you.
Thank you.
And this is a